Where's Schoology? I gotta open up a new tab. Just as a reminder, let me just jump into this one here. This review, I'll put I will put this video that I'm taking right now, like down here with this other review video. Oh wait, there was no. Oh yeah, video down here. And I'll make sure it's noted as it's today's. But these are all suggested problems this is the review that I had a long time ago, before I created this review sheet. All of these problems would be suggested problems. There's the key to it, and there's a video to it. Again, I'm just leaving that all up. If you need extra problems, I would go there. Okay. Yeah, but let's get to it. Okay. I'm just going to go question by question. If you have anything, if you're like, whoa, I didn't understand that, go back to that, do that again. Please stop me, or if I go too fast or something. All right, find the location of the local absolute maximums and minimums. You only need to provide the X values for these. Okay, what is the absolute maximum here? Where does the absolute maximum occur? Where's the highest point? Highest point would be right here at 1, right? Is that still an absolute maximum, even though like it's a discontinuity? Yes. People always get tripped up by that, like thinking. Let me get that right there. Like thinking that it's not actually a maximum or minimum because there's a discontinuity. No. Be careful in saying that. You're right that it is not differentiable at that moment because the limit does not exist. But that doesn't mean that there's not a maximum value. What that means is, like for this particular function, the critical point would not necessarily be the maximum or minimum value. It's actually probably where the derivative doesn't exist. That's probably what's happening right there. Okay? That's why it's a maximum or minimum value. Maximum in this case. Absolute. What's the absolute minimum? Down here, right? This is at -1, -2, -3, -4. Is that also a local? No, because it's an endpoint. Remember that it could be absolute, but not local if it's an endpoint. Okay, let's take a look at the local maximums. There is a high point here. There is a local maximum there. Yeah, there's one at -2. There is one at +1. Is this a local maximum point on the right-hand side? No. Because even though it looks like it is kind of like topping out up there, it's an endpoint. There's nothing happening on the right side of it. It's not defined to the right side. And yes, 1 is a local maximum. Even though it is a discontinuity there, it is a local maximum. Local minimum value. Local minimum value. I see one right here, and I see one right there. Yeah. So -1 and +2. Yeah. Questions about that? Okay. Somebody said, I remember somebody trying to make the argument last year of like, look there though, isn't that point like the highest around? Because it's like leading up here. I see what you're saying on the right side, but you have to take into account this piece over here because directly to the left of 1, there are points right here, right? Maybe it wasn't this exact example, but it was something similar to that. Be careful when looking at those discontinuities. It can be a little tricky. All right, use the closed interval method. The closed interval method. Remember, closed interval method is for the cases where you have a closed interval and it's continuous and differentiable inside of that interval. Now, these are all polynomial on here. Yeah, I guess all of these functions are polynomial, so they're all going to be continuous and differentiable. So perfect. But I am saying on the interval from -2 to 4, find the absolute maximums and minimums. And again, the closed interval method says that there has to be an absolute maximum or minimum along the closed interval if it's continuous and differentiable, either at any of the endpoints or any of the critical points. So you need to test the endpoints, and then you need to test the critical points. Let's see what those critical points are. Find the derivative. 3x squared minus 6x minus 9. Set that equal to 0. Could this ever not exist? because that's the other place for a critical point, right? Could this ever not exist? No, it's going to exist everywhere. It's polynomial again. So you set that equal to 0. Again, the only cases where it couldn't exist are things like logarithmic functions or rational functions or square root functions, weird ones like that. Pull out a 3. Set that equal to 0. Okay, so that looks like it's an x minus factors of negative 3 to get a negative 2. X minus 3x plus 1. Right? Yeah. And again, that's not a 0 because it's just a factor. So x equals 3, x equals negative 1. So those are my critical points. Negative 1, positive 3. Negative 1, positive 3. Okay, now let's figure out what those y values are. Now, be careful. Don't confuse this with the ID test, the increase-decrease test, the first derivative test. When I plug these in, are they going back into the original or to the derivative? Original for the closed integral method. Original. Because what am I truly seeing here? I'm truly seeing how high or low these points actually go, right? What the y values are, because that's going to tell me whether it's an absolute maximum or minimum. Okay, so for example here, negative 2. Negative 2 to the third minus 3 times negative 2 squared minus 9 times negative 2 minus 1. Just double checking I punch that in right. Negative 2 to the third minus 3 times negative 2 squared minus 9 times negative 2 minus 1. Bingo. Negative 3. So I've got this negative 2, negative 3 point that is an endpoint on the left side of this function. Let's plug in negative 1. So we have negative 1 to the third. Got negative 1 minus 3 times negative 1 squared minus 9 times negative 1. Should just punch that in again. Which is positive 4. 3 is going to be 3 to the third minus 3 times 3 squared is 9 minus 9 times 3 minus 1. Negative 28. And then 4. So 4 to the third minus 3 times 4 squared is 16 minus 9 times 4 minus 1. Negative 21. Okay, what's the absolute maximum? Negative 1 comma 4. What is the absolute minimum? 3 comma negative 28. So it just happens to be that these both occur at the critical points. It doesn't have to happen like that. It just happen like this one. Questions about that? Okay, let's take a look at number 3. Compare and contrast Rolle's theorem and the mean value theorem. Be sure to state the similarities and differences in both the hypothesis and the conclusion. Okay, so for the hypothesis, okay, remember that there's one big difference in, let's talk about the similarities though. Okay, hypothesis. For Rolle's theorem and the mean value theorem, they are both continuous and differentiable, right? They have to be both continuous and differentiable. There is one big difference. Well, it's the fact that Rolle's theorem needs f of a to equal f of b. That's part of the hypothesis of Rolle's theorem. It says that it's got to be continuous, differentiable, and the endpoints need to be equivalent. Okay. I guess we could say continuous, differentiable along the interval a to b, right? Continuous and differentiable on the interval a to b. The big difference is that Rolle's needs f of a to equal f of b. Okay. So for the conclusion, Okay, hypothesis and conclusion. The conclusion, okay, the similarities and the differences, really, it might be easier to talk about the difference first. The difference is that in Rolle's theorem, f prime of c is equal to 0, right? In Rolle's theorem, there exists a point c such that f prime of c is equivalent to 0. In the mean value theorem, a little bit more room. In the mean value theorem, it says that f prime of c is equivalent to the endpoints, the slope of the endpoints. F of b minus f of a over b minus a, right? That's the difference in the conclusion. Is that in Rolle's theorem, you're saying that there must be some place in the middle where the derivative goes 0. In the mean value theorem, it says that there must be some point c in the middle that the derivative is equivalent to the slope of the endpoints. Okay. Now, for the similarities here, isn't really like because f of a is equal to f of b, it's really equal to, so there's a derivative. Derivative is equal to the slope of the endpoints. I forgot my L. Slope that's really the similarity. Okay. Now, why is that a similarity? Well, because if I had stated in the hypothesis that f of a was equal to f of b, that must mean the slope of the endpoints is 0, right? So essentially, that's the similarity between them, is that the endpoints are equivalent in Rolle's theorem. It's already set up that way. So the slope of the endpoints is truly 0. So you're still talking about the derivative equaling 0. Okay. Okay, let's take a look at number 4. Verify that the function satisfies the hypothesis of the mean value theorem on the given interval, then find all numbers c that satisfy that conclusion. Okay. Now, what is the hypothesis of the mean value theorem? It's that it's continuous and differentiable along that interval, right? It's continuous and differentiable along that interval. Okay. It is continuous and differentiable on 0 to 4 because it is polynomial. That's how we know. Because it's polynomial, because of the makeup of the function. It's polynomial, so therefore it's got to be continuous and it's got to be differentiable. There's no gaps, breaks, weird things going on. Okay, now that means that I can take f prime of x, which is 10x minus 2, and say that that is equivalent to the slope of the endpoints. 10x minus 2 is equivalent to f of b minus f of a, which I've got to figure those out, right? 5 times 4, let's do 4, 0 is easy. 5 times 4 squared, which is 16, minus 2 times 4, plus 3. So my right end point is 4, 75, right? 4, 75. My left end point is 0, 3. So I can say 75 minus 3. That looks like a 2. 75 minus 3 over 4 minus 0. The derivative is equal to the slope of the endpoints. Well, 75 minus 3 is 72. 72 over 4. What is that? 18, right? Yeah. Add the 2. Okay. Is that value, is 2 in between 0 and 4? Yes. Yeah. So C is equivalent to 2 because that's the conclusion of the mean value theorem. It says there is a point C such that in between there, that point C is equivalent to the derivative at that point is equivalent to the slope of the endpoints. So that value, in this case, is 2. Questions there? Okay. Let's keep on trucking. Here's number 5. Find the intervals on which the function is increasing or decreasing. Use that information to find the local maximum and minimum values. Do not use the second derivative test. Please give the full coordinate for the extreme values. 5 says don't use this second derivative test. 6 says use the second derivative test. So I'm going to need to see both methods. Okay. So essentially, we're finding we're using the first derivative test, basically. All right. That requires me to find f prime, which is 3x squared plus 6x minus 24. And then find my critical points. Let's pull out a 3. And then set that equal to 0. So factors of -8 that I had to get to +4. So that's, +2. That's +4 and -2. So x equals -4 and x equals 2. The number line test is what I'm going to be using, the increase-decrease test or the first derivative test. -4, +2. Show me what values you're testing, please. So here I'm going to test, let's test -5, let's test 0, and then we'll test 3. Now, those go back into the derivative, right? They go back into f prime. So we're going to take 3 times -5 squared is 25, plus 6 times -5 minus 24. And again, I don't care about the fact that this comes out to be 21. I care about the fact that this comes out to be positive. If I plug in 0, this is going to give me a -24. So again, negative. I'm guessing that the next one's going to be positive, but we should run it just to be sure. So plug in 3. 3 times 3 squared is 9, plus 6 times 3 minus 24. And that comes out to be, hey, positive 21. Okay, now that means that I have increase, decrease, increase, right? So I can now say, find the intervals in which a function is increasing and decreasing. Okay, so now I can say that this is increasing on the interval negative infinity to -4, and also from 2 to infinity. It's decreasing on the interval -4 to 2. Then I am going to find the extreme values, the local maximums and minimums. Now, if this is increasing and then decreasing at -4, tops out at -4, right? So that means that there is a local max at -4 comma something, and I'll figure out what that something here is here in a second. And then it goes decrease to increase. So that means local min at 2 comma something. Now, let's figure out what those somethings are. Go back into the original for this. -4 to the third plus 3 times -4 squared minus 24 times -4 plus 6. 86. -4 comma 86. Pretty high up there. And then the local minimum value. I've got 2 to the third plus 3 times 2 squared, which is 4, minus 24 times 2, which is 48, plus 6. So -22. Pretty far down there. Does that make sense? Okay, so that's the first derivative test, right? That's the first derivative test. kind of call it the increase-decrease test, but once we come to the conclusion about the maximums and minimums, that's the first derivative test. So now let's do the same thing with the second derivative test. Okay, still the conclusion is the same, right? I'm still trying to find what the extreme values are. I'm just now using a different method. And the reason we are using this method is because it's pretty easy to find the second derivative. All right, so f prime of x is going to be, why is this out of order? X to the fourth plus 12x cubed plus 15. So 4x cubed plus 36x squared. That's the first derivative. While I'm at it, let's find the second. So that is 12x squared plus 72x. Okay, now remember, you're still finding the derivative. Sorry, the zeros of the first derivative. So set that equal to 0. Let's pull out a 4x squared, leaving us an x plus 9. So that means this gives me an x equals 0 and an x equals negative 9. You follow me there? Those are my two zeros. Those are my two critical points. Is the possibilities of being absolute maximums or minimums. Now, the second derivative test says, okay, plug those guys right into here. Let's find f double prime of 0. Well, what happens when I find f double prime of 0? What do I get? I get 0. I'll come back to that in a second. Let's find f double prime of negative 9. Well, when I find f double prime of negative 9, that's 12 times negative 9 squared plus 72 times negative 9, which is 324. I really don't care about that value. I care about the fact that it is positive. Now, if it is positive, that means it is concave upward at that point, right? And if it is concave upward at that point, a happy face, that means it's got to be a local minimum value, right? So that means it's a local minimum at negative 9 comma something. Right? We'll figure out what that something is. Did it say to find the full coordinate? Yes. Now, this weird piece here, remember that it was, if it's positive, it's a local minimum. If it's negative, it's a local maximum. So what does that imply about the fact that it's 0? It's neither. It's neither here, right? It is neither there. So what is happening there? Maybe an inflection point. Maybe it's a point where it kind of bends through, right? We don't know. We don't really care. We just know that if it comes out to be neither positive nor negative, it's nothing. It's not an extreme value. Okay. All right. So let's finish this off. Negative 9 I've got to plug in. 15 plus 12 times negative 9 cubed plus negative 9 to the fourth. 15 plus 12 times negative 9 cubed plus negative 9 to the fourth. That's going to be a giant number, negative 2172. We good there? And our last one, the big guy. I'll reserve a whole page for these ones, whenever it's on a quick test. Let's give you a whole blank page for it. Find the intervals of increase, decrease, find the local maximum, minimum values, find the interval of concavity, identify any inflection points, and then sketch the graph. Basically, do everything that we've learned. All the stuff. Do all the things. Okay, first thing, increase, decrease, which requires the first derivative. So f prime of x is 3x squared minus 12. Okay, pretty simple first derivative there. Awesome. Pull out a 3. So that's x squared minus, whoa, I almost said 12 again, 4 equals 0. So x squared minus 4 equals 0. Be careful here. Plus or minus 2, right? Don't forget about the plus or minuses. You're going to be removing half the work if you forget about the plus or minus. Okay, we do our number line test. Negative 2, positive 2. Let's say we're going to do negative 3, 0, and 3. Again, this is the first derivative test that I'm doing here. All right, plug that back into the derivative. 3 times negative 3 squared minus 12. It comes out positive. I'm guessing 0 comes out negative. Let's check. Yep. Negative 12. Let's say 3 times 0 squared is 0 minus 12 is negative 12. Now, if we plug in 3 here, let's think smarter, not harder. That's going to be the same thing as negative 3, right? Because I square it. So that's going to still be the same thing that I got, which was 15 positive. Okay, so now I can start compiling my answers. This is increasing on the interval negative infinity until negative 2. And also from 2 to infinity, it's decreasing from negative 2 to positive 2. I have my maximums and minimums now, right? There is a local maximum. Where's the local maximum? It goes up to down. Yep. Increase to decrease at negative 2, right? Increase to decrease, so it tops out at negative 2 comma something. There is a local minimum at, okay, look, I'm decreasing, and then at 2, I start to increase, right? That is a local minimum point at 2 comma something. Let's figure out what those things are right now before we move on. Plug in negative 2, that's negative 2 to the third minus 12 times negative 2 plus 2. 18. Let's plug in positive 2. 2 to the third, that's 8. Minus 12 times 2 is 24. Plus 2. Negative 16. Negative 14. Okay, so there is increase, decrease, local maximum, minimum values. Let's find the intervals of concavity now. And for that, I need my second derivative. So f double prime of x is 6x. Ooh, sweet, nice and easy. So x equals 0, right? Find the zeros of 6x equals 0. So that means I take another number line here. And I can find, okay, let's just use negative 1 and positive 1. Run those through my second derivative. Plug in negative 1, I get negative. Oh, well, negative. Oh, there. Plug in positive 1, I get positive. So that means it is concave upward from 0 to infinity, concave downward from negative infinity to 0, which means if it switches concavity at a certain point, that's the inflection point. So there is an inflection at 0 comma something. Let's figure out what that something is. 0 comma 2, the y-intercept. Now, all that information is used to graph now. Okay. Now, let's see. What are my critical x values? Negative 2, positive 2, and 0, right? Negative 2, positive 2, and 0. So I'm going to say, just a sketch, remember. So 1, 2, 1, 2. Okay. What are my y values that are important? I've got an inflection point of 0, 2. Looks like I need to go all the way up to 18 and all the way down to negative 14. So let's just go by, let's go by tens. 10, 20, negative 10, negative 20. Again, scale it however you need to. Yes? Because I plugged 0 back into my original function. Yeah. Okay, so I know there is a, maximum at negative 2, 18. So some up here. Again, this is just a sketch. Again, I need to see the points where there are maximums and minimums, but I'm not going to be, too picky. 2, negative 14, somewhere down here. There is an inflection here. I know that it is concave upward from here, bottoming out here. I know it's concave downward. There. Yeah. General trends. I could take it one step further. I think we might do this a little bit later on, closer toward the end of the chapter. Couldn't I find the zeros of this function as well? If I really wanted to figure out a better picture of where it crosses the x-axis. I guess I could. I guess I could go back in and find the zeros of that, but that would be a little difficult because it's cubic. If it's quadratic, that'd be a little easier. But yeah. Good there? Cool. All right, let me stop that video.